So we're now done talking about the way that the Java parallel streams works with respect to things like splitting and some of the processing steps, like being able to expand the size of the threads in the common fork join pool and so on. And now we're going to start taking a look at how results are combined. So we'll reach the final phase in the split, apply, combine phase. We're going to focus on combining. And we'll have two different parts to this. The first part here is we're going to talk about how reductions can be performed to combine partial results into a single result. And the key thing to note here, and we'll talk about this more in the next set of slides, is that reduce expects immutable objects, whereas collect expects mutable result containers. So let's go ahead and take a look at this. So remember, after the chunks are processed, then we're going to combine everything together into a final so-called reduced result. So that looks like this, where you can see that we split, split, split using splitterators. We process, process, process using the common fork join pool. And now we're basically joining, joining, joining until we get a final result. For the moment, we're going to assume that we have a non-concurrent collector. We'll talk about concurrent collectors later, probably next week. Note that the join occurs in a single thread at each level. In other words, the parent at any given point joins its children together until we end up with a final result. As a consequence of this, even with non-concurrent collectors when used with parallel streams, there is no need for any synchronizers. You don't have to put any locks in your code. That'll be handled for you by the underlying framework. The key thing to remember, however, is that different terminal operations combine partial results in different ways. And these differences matter for parallel streams. They don't really matter for sequential streams because they're not combining things. So here's what you need to remember. Reduce creates a new immutable value and expects to have immutable values. So here's a simple example. We've looked at this before, but now we're going to look at it from the point of view of immutability, where you're going to generate the nth factorial by using a long stream from 1 to n, running things in parallel. And of course, that'll split up into little chunks. I didn't get it all the way down to chunks of size 1, but you can imagine it goes down to chunks of size 1, which are trivially returned. And then what's going to happen is we do pairwise reductions using the reduce method. And so the reduce is a terminal operation. We give it the identity value for product, which is 1, and then we give it a lambda expression, which multiplies two immutable values together and yields a new immutable value. And you can see here that all these things take place sequentially, but all in parallel. So the operations of multiplying things together run sequentially, but all of those different multiplications run in parallel. So as you can imagine, 1 times 2 is 2, 3 times 4 is 12, 5 times 6 is 30, 7 times 8 is 56. You probably knew that already. And then what we're going to do is we will continue to reduce these immutable values and produce a new one. So 2 times 12, 24, 30 times 56 is 1,680. And then when those things are reduced, we get 40,320. In contrast, collect mutates an existing value. So here's an example that we're going to take a look at. This is one where we're going to get all the words in the works of Shakespeare, and we're going to split them up into words. And I actually have a much more complicated regular expression here that you'll see. And then we're going to run this as a parallel stream. And then we're going to collect all the results together. And the thing to remember is collect will create a mutable container. And in fact, there'll be collects that are taking place at multiple points in this tree of tasks. If you remember our discussion about how parallel streams works internally, you end up with a tree of tasks. And for this particular version, using a non-concurrent collector, collect will collect into local tree sets, and then those tree sets will be merged together multiple times as the recursion backs out in order to come up with a final tree set. So that's basically what's happening. And the key thing to note here is that tree sets are mutable. And we're also going to take a look later about concurrent collectors. And this is kind of interesting. I'll give you a preview of coming attractions. So notice that with non-concurrent collectors, we're basically doing localized collectors at multiple places to merge things together. And so we keep merging two tree sets together, and we end up with one final tree set. But there's going to be lots of merging taking place. In contrast, with concurrent collectors, there is no merging. What happens is you have a single thread-safe concurrent result container, concurrent mutable result container, and the parts of the stream that are processed in parallel will accumulate into that one and only mutable result container. And so we'll take a look later. We probably won't have time to do that today, but when we take a look later, you'll see how that can actually speed things up when you have a large number of elements being run in parallel, especially with complicated collections like tree sets or maps or hash sets or hash maps and so on, where there's actually a fairly high overhead for merging things back and forth. So that's the first part of this discussion.